Welcome back to this new session. We're still in the course Masterclass in Project Management. We are talking about linear programming and projects. And in this lesson, this video, I will talk about the maximization problem, and we use it in an application where we're going to define the inequalities and the objective function. Very important when we start with a linear programming problem that we identify the relevant inequalities and, of course, the objective function. We will start with describing the problem. In our case, we will be looking at the production of two bicycles, fancy and sporty, and we have a description in which we find all the conditions that we need to resolve this as a linear programming problem. We have two processes. Process 1 is the preparation of the bicycle. Process 2 is the assembly. And then we also have the process limit. So with these 3 points, we're going to find all the relevant linear programming equations or the inequalities. Finally, we'll have an overview of all the inequalities and the objective function. In this case, we're talking about a maximization problem. So in our solution here, we have to find. So let's start with describing the problem. Now, this is a description. You may get it in different ways, but I summarized what we are going to do. We have a factory, we produce fancy and sporty bikes. Process 1 is the preparation of the separate parts. Process 2 is the assembly of the bicycle. Team 1 works on process 1, has a capacity of 1,440 hours. Team 2 works on process 2, has a capacity of 600 hours. Process 1 takes 6 hours for fancy, 4.5 hours for sporty. Process 2 takes 3 hours for fancy and 1.5 hours for sporty. We do not want to have more than 300 sporty and 175 fancy bikes in stock. The profit on sporty is 100, and for fancy it's a profit of 165. Now we want to find the optimal mix, the mix that maximizes our profit. So we're going to look at those two processes separately. Let's have a look at process 1. Here we see process 1 is the preparation of the separate parts. We know that team 1 has a capacity of 1,440 hours, which means that all the work they're working on the two bicycles, fancy and sporty, cannot exceed 1,440 hours. It can be equal to 1,440 hours, but it cannot be more. When we look at the process, there are two data that we need here for creating a fancy bike. For preparation of the fancy bike, the team needs 6 hours and 4.5 hours for sporty. We can put all of that in a table, and we find the table here. We have the different bicycles, we have the variables. We call X sporty and Y is fancy. For process 1, the production time is 4.5 for sporty, and for fancy it is 6. So we find here these parameters. We can write the inequality. We can express that we cannot work more than 1,440 hours. So we can say 4.5x plus 6 times y has to be smaller or equal than 1,440 hours. It means whatever combination of sporty and fancy we will be combining, it will be basically not, or it should not exceed the 1,440 hours. The next thing is the process 2. That process 2 is the assembly of the bicycles. We're going to look at the second team. We have a team with a capacity of 600 hours, and we have 3 hours for fancy and 1.5 hours for sporty. We can put this again in our table. So we have 1.5 and 3 for the different items, and we can create, or we can write the inequality. In this case, 1.5x plus 3 times y smaller or equal than 600. which basically expresses that whatever combination of x and y we are working on, we should not exceed 600 hours. The next thing are the process limits. We have some limits that we have. We do not want to have more than 300 sporty and 175 fancy bikes in stock. So we have to add this element to our table. We have a maximum here, sporty 300 and fancy 175. So here we have to say x has to be smaller than 300 and y has to be smaller than 175. Now we can put all the equations together. So we have basically the initial overview. We have the different bicycles, sporty, the data that we use to create the different equations. We also have the equations in summary: 4.5x plus 6 times y smaller than equal 1440 and so on. And these are the equations that we found before. We have to add the non-negativity condition, and it's not described anywhere, but we have to state that the variables x and y are positive. Lowest value can be 0, we don't produce anything, but we cannot have it negative. And of course, we also have to have the objective function. Here we have to express the profit of the different bicycles. So we will have 165 for x, for sporty. For fancy we have 100. So we have 165x plus 100y. When this we have to maximize. So that was it for this first part in our maximization problem, where we are determining the inequalities, we are looking at the limits, and we define the objective functions. Thank you very much, and I'm looking forward to seeing you in our next videos. Bye bye.